Okay, so new ij, we are talking about component. I is component and j is the reaction number, right? So we have reaction 1 and reaction 2. So new 1 1, that means component 1 and reaction 1. What is component 1?
कार्बन डाइऑक्साइड सर।
कार्बन डाइऑक्साइड एंड रिएक्शन 1, so क्या हो जाएगा उसका न्यू?
-1।
-1, right? So new component 2 reaction 1 क्या हो जाएगा? Component 2 is what? Component 2 is hydrogen, right? So what is the new for hydrogen in the first reaction?
-3।
-3. New component 3 for the first reaction?
+1।
+1. And new for component 4 in the first reaction?
+1।
Okay, so now if we take second reaction, this is reaction 1. New 1 in second reaction is how much?
-1।
-1. New 2 in the second reaction is how much?
-1.
New 3 in the second reaction is how much?
+1.
New 3. 3 is what? Component 3 is same for both the reactions. You have to remember that. Numbering has to remain the same. New 3 is what?
0।
0. It can be 0 because we're talking about two reactions simultaneously, so it can be 0. New 4 in the second reaction?
H2O।
उसका H2O नहीं बन रहा है क्या for second reaction में?
अच्छा +1 सॉरी।
+1. Now we have new 5 in the second reaction. क्या हो जाएगा उसका?
+1।
+1. So now there has to be a new 5 in the first reaction also, right? There cannot be something without something, right? So new 5 in first reaction क्या हो जाएगा?
0।
0. So you have to write new for each component in each reaction. That is new ij. That's what we are writing, right? For reaction 1 is for reaction 1 is for reaction 2. समझ में आया सबको ये?
यस सर।
Right? So now what we need to do is we need to reaction 1, that is equal to new 1. क्या हो जाएगा new 1? Reaction 1?
-2.
Summation of new ij. ij नहीं होगा, I1. All components in reaction 1. So it is -3 +1 +1 +0. ठीक है? Summation of all these things. And वो -1 ऊपर वाला. Right? One component 1 is -1, -3, 1 +1 +1 and 0. तो कितना हो जाएगा ये? How much is this?
-2।
So now we have to find out new 2, that is summation of I for second reaction. -1 -1 +0 +1 +1. Agree?
0.
Right? So now we have everything. We are not just need to substitute in that equation, right? Equation क्या था अपना? So this is our equation, right? yi is equal to ni0 plus summation of nu ij into epsilon j upon n0 plus summation of nu j into epsilon j, right? ni0 कितना है? Suppose I want to write y of पहला कंपोनेंट क्या था? CO2. If I want to write y of CO2, CO2 का initial components कितना था? Initial moles कितना?
Three.
CO2 3, right? 3 plus summation of nu ij, that means component 1 all components into reaction 1, right? No, component 1 in both reactions, right? So this summation over reactions. So component 1 in reaction 1, sorry. So component 1 reaction 1 is minus 1 into epsilon 1 plus component 1 reaction 2, right? Again minus 1 into epsilon 2. बराबर है क्या? Divide by n0. n0 कितना है? Initial moles total. n0 is 3 plus 5 plus 1, right? So n0 is so 9 plus summation over j, nu j, this is nu j, right? हमने लिया is actually nu j. So minus 2 into epsilon 1 plus again minus 1 into epsilon 2. Is this correct?
No sir, epsilon 2 के लिए 0 है.
Oh sorry, 0. Sorry, 0. So, ठीक है? Any other corrections?
No sir, correct है.
So this is now equal to YCO2 equal to 3 minus epsilon 1 minus epsilon 2 upon 9 minus 2 epsilon 1. ठीक है? Any questions, doubts on this equation? समझ में आ लोगों को कैसे करने का है? Okay, so now we need to do the same thing for all the other components. So y second component क्या था अपना? Y hydrogen. If you look at Y hydrogen, initial moles of hydrogen कितना है? 5 moles plus. Okay, now what we need is hydrogen के लिए reaction 1 में कितना है? 2, that is minus 3. और reaction 2 में minus 1. और डिनोमिनेटर क्या हो जाएगा?
सर सेम रहेगा.
Same रहेगा. So we don't need to do it again and again. So this is going to be 5 minus 3 epsilon 1 minus epsilon 2 upon 9 minus 2 epsilon 1. ठीक है? Third component was methanol. Methanol initial components कितना था? What is the initial moles of methanol?
0.
0. So 0 plus new methanol in the first reaction is 3, right? प्लस
नो सर 1 आएगा ना, उसको हमने
सॉरी 1 रहेगा 1 प्लस सेकेंड रिएक्शन में इथेनॉल बन रहा है क्या? नहीं बन रहा, राइट? सो इट इज 0 upon 9 minus 2 epsilon 1. So it is epsilon 1 upon 9 minus 2 epsilon 1. ठीक है? So next component is y of H2O. Initial moles कितना है H2O का? What is the moles of H2O initially?
1 mole.
1 mole. So initial is 1 plus अभी फर्स्ट रिएक्शन में H2O कितना बन रहा है? Mu is 1, right? So 1 epsilon 1 plus second reaction में भी H2O बन रहा है. You have to write that. So again 1 mole, 1 nu है उसका. So 1 into epsilon 2 upon 9 minus 2 epsilon 1, that is nothing but 1 plus epsilon 1 plus epsilon 2 upon 9 minus 2 epsilon 1. ठीक है? Any questions on YH2? Because it is there in both the reactions, we have to add for both. And finally we have to see Y of CO, carbon monoxide, the second reaction. Initially कितना है YCO?
0.
0, right? So initially it is 0 plus first reaction में मिथनॉल बन रहा है क्या? CO बन रहा है क्या? नहीं बन रहा है, राइट? मुझे सेकेंड रिएक्शन में बन रहा है. सो प्लस 0 इंटू एप्सिलॉन 1 प्लस सेकेंड रिएक्शन 1 इंटू एप्सिलॉन 2 अपॉन 9 माइनस 2 एप्सिलॉन 1. सो एसेंशियली एप्सिलॉन 2 अपॉन 9 माइनस 2 एप्सिलॉन 1. ठीक है? Any doubts, questions on how to use this formula? First subscript is component, second subscript is reaction number. ये समझ में आ गया तो you can easily use this formula for any reaction, any number of reactions. 2, 3, 4, 5 जितने भी reaction होगा you can use it. ठीक है, there are no questions. Let's proceed further. Now we're going to look at criteria of equilibrium for a chemical reaction. You have seen criteria of equilibrium for criteria of equilibrium general derive किया था, right? हमने phase equilibrium के लिए ये निकाला था dg और change in Gibbs free energy at constant temperature and pressure is equal to 0. But this is a general criterion. It's not only for phase equilibrium. So I can remove this thing here. This criteria of equilibrium. We don't say it is for phase or whatever. So equilibrium में ये applicable रहता है. So when a chemical reaction occurs, there's no change in Gibbs free energy of system, provided change takes place at constant temperature and pressure. We always say it is constant temperature and pressure. And we are always looking at systems where the pressure and temperature are constant. So let us consider reaction at equilibrium given by this equation. A times A plus B times B is L times L plus M times M. Now there is an infinitesimal change, there is very small change taking place. The increment number of moles is, suppose it is dNA for component A, dNB for component B, dNL for component L, dNM for fundamental relation of changes for changes. We have seen this derivation is essentially equation 2. dg total is equal to Vt into dP minus St into dt plus summation of mu I into dni. And at constant temperature pressure, these two terms will go, and what we get is dg is equal to summation of mu I into dni. ठीक है? Any questions on equation 3? Okay, so for reaction 1, we can write this equation 3 we get dg total will be summation of mu I dna, that means mu l product का into dnl plus mu m into dnm plus mu a into dna plus mu b into dnb, right? And we know by definition we have defined this, right? dni is equal to mu I into d epsilon by definition of epsilon. So substitute 5 and 4, and what we'll get is dg, T at constant temperature and pressure is equal to nu L into mu L, d epsilon बाहर आ जाएगा, plus nu m into mu m plus nu a into mu a plus nu b into mu b, whole bracket into d epsilon, right? So now we know nu L is L, nu m is m, nu a is minus a, and nu b is minus b. So we substitute that in equation 6 and we get equation 6. Stoichiometric numbers, we know that L and m are positive for product.
सर वॉइस ब्रेक हो रहा है.
And negative for reactant. Okay, can you hear me now? Hello. Network
Yes,
issues
sir.
are. Network had gone for a toss. And someone of you muted me also. Don't mute me. Okay. So let's see. दिख रहा है क्या ये? एक मिनट. Let me see. Start again. Hello, can you hear me? Hello.
Yes, sir.
और वो दिख रहा है क्या? Can you see this?
Yes, sir.
Okay. So something has gone wrong on PC. वहाँ पर नहीं चल रहा है. Okay, so if you can see this, let's continue. So what we get is equation 6, right? When you substitute the stoichiometric numbers L, M, and minus A and minus B, and for infinitesimal change, equation 6 gives Tg is equal to, there is nothing but summation of mu I into nu I into nu I. This is nu I. This is mu I into d epsilon. Okay. So at equilibrium, we know that equation 1 applies, right? Which is dg at constant temperature and pressure is equal to 0. So it's the summation of mu I into d epsilon has to be equal to 0. Or we can say that summation of mu I into nu I equal to 0 because d epsilon will not be 0. Right? Extent of reaction has to be there if the reaction is taking place, right? So d epsilon is 0 at only at the start of the reaction. As the reaction proceeds, d epsilon will have okay. So now if you use this equation 8 and write for reaction 1, we'll get what? L product into mu L. This mu I for a product is L into mu L plus mu I for a product M is M into mu M minus A is for the reactant into mu A minus B into mu B is equal to 0. Right. Or we can get equation 9 by combining these two and taking minus out. Okay. So equation left hand side of equation 9 is free energy change of reaction. Therefore, delta G is equal to 0 at equilibrium. Any questions? Okay. So let us look at a reaction where A goes to B at equilibrium. Epsilon is extent of reaction. Change in number of moles of A is equal to dNA, nothing but nu A into d epsilon. Or in this case, nu A is -1, so it is minus d epsilon. And change in number of moles of B is dNB is equal to nu B into d epsilon. In this case, nu B is +1, so it is plus d epsilon. So dg total is equal to summation of mu I into d epsilon. Or if we substitute these two, we can get mu B minus mu A into d epsilon. Okay, so we can write, if we take this out here, we get this double G by double epsilon at constant temperature and pressure is equal to mu B minus mu A. And this left hand side is nothing but slope of the Gibbs free energy extent of Gibbs free energy curve. Let's see. इधर करना पड़ेगा. Anyway, ये curve move नहीं हो रहा है. I'll move it later. So what we are doing is we are looking at Gibbs free energy on the y-axis versus epsilon on the x-axis, and we have curve like this, something like this. And what we are getting is double G by double T at double G by double epsilon at constant temperature pressure is equal to 0 at this point. This is the equilibrium condition. On the right hand side, it is greater than 0, slope is positive. On the left hand side, it is less than 0, slope is negative. This is a typical G total versus epsilon curve. Okay. So reaction will proceed in the direction of decreasing Gibbs free energy because we see that forward reaction is A goes to B. This will take place when mu A is greater than mu B. We've seen this, right? Okay. So when mu A is greater than mu B, this term will be negative. Or this term will be negative. Reaction taking place, because we are talking about equilibrium reaction. This is a reversible reaction. So in certain situations, the forward reaction takes place. Certain situations, the reverse reaction takes place. And at equilibrium, what happens at equilibrium for reversible reaction? पढ़ा है कि नहीं केमिस्ट्री में? Hello. Can you hear me? So केमिस्ट्री में पढ़ा है नहीं? रिवर्सिबल रिएक्शन में क्या होता है एट इक्विलिब्रियम? नहीं पढ़ा है? इक्विलिब्रियम पढ़ा है ना आपको मैंने? What is equilibrium?
Rate of forward reaction equal to rate of backward.
Rate of forward reaction is equal to rate of reversible reaction, right? So in this case, equilibrium यहाँ पर है. When this slope is zero, this is equilibrium condition. And when mu A is greater than mu B, forward reaction will take place. When mu B is greater than mu A, reverse reaction takes place, because that is what it shows right here. Slope is mu B minus mu A. So and mu A is greater than mu B, forward reaction will take place, and when mu B is greater than mu A, reverse reaction will take place. And at equilibrium, mu A is equal to mu B. That's what it is. It will be zero only when mu A is equal to mu B. The slope is zero when it is equal. Chemical potential. Okay, any questions, doubts on this? समझ में आया लोगों को? I want to see hands. कितने लोग को नहीं समझ में आया? आवाज आ रहा है कि नहीं आ रहा है मेरा? Can you hear me?
आ रहा है सर.
समझ में आया? Zero. That means mu A is equal to mu B. Our reaction will take obviously.
Sir, now
Issue is there. Can you hear me now?
Yes, sir.
Okay. और वो दिख रहा है क्या? ये Can you see this? Any
Yes, sir.
questions on this? So equilibrium में mu equal to mu b रहेगा, right? And if mu a is greater than mu b, then forward reaction will take place. And if mu b is greater than mu a, the reverse reaction will take place. In this condition, it is forward reaction. This condition, it is reverse reaction. Right? So, and this is mu a is greater than mu b. That means this is negative. It is forward reaction. यहाँ पर mu a is less than mu b or mu b is greater than mu a. So this is positive. This is reverse reaction. ठीक है? So this is a case of reversible reaction. If the system is not in equilibrium, the reaction must be irreversible. There are many irreversible reactions. Examples याद है किसी को irreversible reactions के? Anybody remembers?
Formation.
Formation नहीं, reaction की बात कर रहा हूँ मैं. If I take H2SO4 plus NaOH, is this reversible reaction? केमिस्ट्री पढ़ा कि नहीं पढ़ा उन्होंने?
Irreversible है ना सर?
This is a reversible reaction. Normally, most of the inorganic reactions are irreversible. Many organic reactions are reversible. So you'll see most of the times what you'll see is when you are talking about equilibrium, we are talking about the limit of conversion, right? Maximum कितना reaction हो सकता है, because equilibrium में reversible and forward reaction होता है और reversible reaction होता है. There is certain condition up to which the conversion will take place or Z will be maximum. उससे ज़्यादा नहीं होगा कभी conversion for a reversible reaction. Okay, so that is why we are looking at what is the criteria of equilibrium and when we can say that we are going to have a feasible reaction. That is the next step we are going to look at. Okay. This before, right? G is equal to H minus Ts and H is equal to U plus PV. So we can substitute this in first reaction equation and get G is equal to U plus PV minus Ts. And if you take total derivative, you get dg equal to du plus pdv plus vdp minus tds minus sgt. Right? और ये du एक साइड में लिया और बाकी सब दूसरे में लेके आया तो what you get is du is equal to dg minus pdv minus vdp plus tds plus sgt. Right? And at constant temperature and pressure, this term becomes 0 and this term becomes 0. And what you get is du is equal to dg minus pdv plus tds. Now first law says dq is equal to du plus dw and second law says ds is greater than or equal to dq by t. So if you combine these two, what you get is tds is greater than or equal to dq, which is equal to du plus dw. Or you can say du is less than or equal to TDS minus dw, and dw is always pdv work, so it is du is less than or equal to TDS minus pdv. If you combine equation 1 and 2, left hand side is same du. So what you'll get is TDS minus pdv is greater than or equal to dg minus pdv plus TDS. So these will cancel out, and what you get is dg is less than or equal to 0, which we had proved before, right? Equality is for equilibrium or reversible reaction, and this less than is for irreversible. Okay. Any questions so far? Okay. So now we know that criteria of equilibrium is essentially mu A should be equal to mu B. That means chemical potential of reactant should be equal to chemical potential of product. Then it is equilibrium. If mu A is greater than mu B, it is forward reaction. If mu B is greater than mu A, it is reversible reaction, reverse reaction. Okay, any questions on this derivation? Criteria of equilibrium for a chemical reaction. Yeah, अगर question नहीं है तो let's move on to the next topic, which is equilibrium constant. Okay, so when you talk about equilibrium reaction, we intend to define an equilibrium constant, and that is defined as K is equal to K subscript of A. So we are defining based on activity coefficient or activity. So it is defined as activity of component L, that is product, raised to the power of stoichiometric number of component L or product into activity of component M, which is product, raised to power of stoichiometric number of M, divided by reactant का activity of A raised to power of stoichiometric number of A into activity of reactant B raised to power of stoichiometric number B. And this is written as pi of AI raised to the power of nu I. So when you write this thing, it means this thing. This is a short way of writing this definition. AI is activity of I and nu I is stoichiometric number. And we know that AI is equal to Fi bar upon Fi0, where Fi bar is fugacity of I in solution, Fi0 is fugacity of pure component at standard state. So substitute 2 in 1, right? What you'll get is pi of Fi bar by Fi0 raised to power of nu I. So we're just substituting for AI here, and we'll get equation 3. This is another definition of K. So this is K in terms of activity, equilibrium constant instead of in terms of activity. This K in terms of fugacity, equation 3. For gases, standard state is pure component at pressure, where Fi0 is equal to 1, that means low pressure. So equation 3 gives K is equal to, so if Fi0 is equal to 1, so what you get is pi of Fi bar raised to power of nu I, which is known as, defined as Kf, that means fugacity, K based on fugacity. Like we had here, Ka, the definition of K based on activity was Ka. So K defined based on fugacity is Kf. But for liquids, K is not equal to Kf because this is not equal to 1 for liquids, right? Right. So we can write another definition of K, which is Kp, which is based on partial pressures, similar to what we have seen for fugacity, pi into pi of partial pressure of component I raised to the power of nu I. And this is only for gases. Then another definition is based on fugacity coefficient, where fugacity coefficient K phi I is nothing but Fi bar upon Pi bar. So substitute equation 6 in equation 4, this one, F is equal to phi into pi bar. What you get is K is equal to Kf over equation 4 is equal to pi of phi I bar into pi bar raised to the power of nu I. Or we can separate it as K is equal to Kf pi of phi I bar raised to the power of nu I to pi bar raised to the power of nu I. That is equation 7. And then we define another K based on phi. This K phi is nothing but pi of phi I bar raised to the power of nu I. And so we get K is equal to Kf is equal to K phi into Kp. This is Kp, this is K phi. And this equation is applicable for gases. Equation 8. And if gases behave as ideal gases, viscosity coefficient is equal to 1 by definition. So what we'll get is K is equal to Kf is equal to Kp for gases. We have various definitions of K. We are going to use these in our calculations later on, but they are just definitions. This is how we define equilibrium constant based on different parameters like pressure, viscosity, activity, viscosity coefficient, depending on what is available, what data is available. If pressure is available, you can use partial pressure. If is available, use available. Viscosity coefficient is available, use viscosity coefficient. So there are different ways of calculating K. Okay. Any questions? They're just definitions. इसमें कुछ समझने का नहीं है. Defined है. This is the way it is defined. These are not any conceptual things. Just definition of K equilibrium constant in different terms. ठीक है. Any questions? Can you hear me?
Yes, sir.
Okay. So we'll stop here today, and we'll meet again tomorrow. Yeah, Dikshita, you were saying something? Questions again?
No, sir.
Okay. ठीक है. So have a good day. We'll see you tomorrow.